want less strain.
More strain is also better. If you have more inhomogeneous broadening, is better.
It's better, that's what I was saying. So you put an ion which is higher ionic radius, still it's fine.
Higher the
We have tried higher.
I will show you some examples. So that's where the glasses come into picture. So that's the kind of information you get. People demonstrated. They stored lots of images, they retrieved all sorts, they have been demonstrated, but only problem is liquid helium. Because that's where this problem bottleneck. Okay, now I'm going to show you the holes. Probably this should have come earlier. So this is the principle. All you do is, so at one time, few years back, one guy came and said, what are you doing? I said, I'm hole bending. Oh, you are doing only absorption spectrum. That means I deal with only 2 levels. Okay, nothing else. No, he said you are doing only absorption. See here, when you record the absorption, you get a peak like this. This is frequency versus intensity. Okay? So this broadening is related to the inhomogeneous broadening. So let's say you take a laser beam. So let's assume this inhomogeneous broadening is in gigahertz. You take a laser whose line width is kilohertz. So that means you selectively excite one set of ions. You selectively modify them. When you modify, it can be photochemical, it can be photophysical, it can be population rearrangement. When you do that, they don't absorb light anymore. When they don't absorb light anymore, you record the absorption again, you see a hole. That's what happens at that particular system. We call that optical hole burning. It's not a physical hole. You don't damage the material. Everything looks intact. Okay? You change the laser frequency to another spot, you can burn another hole. Then how do you are sure you are burning a hole? So when you are doing the hole burning, if you look at the material, the emission intensity keeps on going down. You can see this one way you monitor with your eyes. Okay? The monitor intensity versus time, the emission intensity goes down. And there are many other techniques you can also do. There is something called sideband spectrum, RF optical double resonance. You can do that. That's an IRF technique. In fact, that's the one we tried when we were in Agro. We were doing the RF optical double resonance. We were doing mainly through this population rearrangement among hypertime. And after coming here at A&M, we were doing photophysical, photochemical. That's what we tried. I will show you some results what we did at A&M. So, photo bleaching of a homogeneous line from an inhomogeneously broadened absorption spectrum causing the appearance of a hole in the reflection spectrum. That's all. And then you can do a whole body. So these are some of the criteria. You need a zero phonon line. You need homogeneous line width that's less than inhomogeneous width. You need a narrow laser. It has to exhibit fluorescence line array. Those are the criteria for the material to exhibit whole body. Okay. So now we don't have time. I will show you some of the work in some of the things we tried: silicates, borosilicate, germanites, and telluride. And see here, there's the hole. This was bonded 10K glass. And for example, in germinate glass, see here, is an example for a photophysical hole body. When you have burn a hole, the surrounding environment changes. I showed you with this cartoon. Initially, the surroundings have one particular crystal field, that's the energy level. Surrounding environment changes, the crystal field changes, the energy level will shift. So the energy level which was absorbing before doesn't absorb anymore, you see a hole. But you see absorbed at a new frequency. That's why you see a hole here, you see an anti-hole. Okay? So that is due to photophysical mechanism. And I will show you here in telluride glass. See, in this glass there are electrons floating around inside. So whenever we shine the material with the laser beam, one electron is moving from one place to the other. As a result, if you look at the europium, the electron and the europium distance is changing. As a result, the electric field changes, we have a hole. Another mechanism we identified here. And so then this is the one nanostructure where ISRO is doing, and now Victor, they are participating here. can build more efficient software amplifiers, displays, converters. All these are applications. And why we do nanostructures? Around you do with materials with the metallic particles that will modulate the refractive index, you can increase the local field, higher quantum efficiency, all that. And physical characteristics. Glasses are easy to make, they have better material properties, but the quantum efficiency is low because the vibrational frequencies are higher. In fluorides, the vibrational frequencies are smaller. So you want to take advantage of the fluorides and the optical and mechanical properties of glasses. So we make nanostructures, fluorides, crystallites in glasses. That's what Hindu is doing. And then Victor is doing metallic nanoparticles in glasses. And here we do something called heat treatment. That's what we use for burning walls. And there are some other applications of this. And probably can leave. So this is all got started with this 2 years back. We were trying, we didn't have anything to monitor. So we created microstructures instead of nanostructures. So when you create microstructure, glass is not going to be transferred. That's what we ended up getting. So later on we tried to improve it based on that, and then Hindu tried in Volvium, she got some nanocrystals. See here, this printed F3 here, this energy gap is small. The glass matrix, this level is not going to emit because this energy gap is small, the phonon frequency is large. So she chose a mixed glass where the phonon frequency is not that large, but at the same time it's not that low. So you see some emission here, but when you crystallize the Volvium particles, you see enhanced emission from this level. That's what she did. And see, these are some of the structures. You can do all kinds of things inside. See here, the dotted line is the emission in the azimate glass, and the solid line is the emission in the crystallized glass. So when you make nanocrystals, the emission intensity increases because of crystalline environment, so the emission intensity increases. But at the same time, you have glasses, you are easy to make. So you take advantage of glasses and the advantage of crystals both. And maybe in lack of time, we'll go a little faster. So the FEM glass, in the beginning you don't have, later on started getting this light. Once you do the heat treatment, and now see here, this dark curve is the emission from the azimate glass. This red is the emission intensity in crystallized glass. So once you make the crystalline, your emission intensity increases because you are taking advantage of the fluorides and you are making glasses. You are getting double reactors. So basically that's the advantage of the nanostructures. And the same thing here, we made some depth profile, so you have more crystallized here. As you go deeper, they are less. And I will show you some where this is X-ray diffraction measurements to show you that yeah, it does have crystals. If you don't have crystals, that's how you get. If you have crystals, you see the sharp spikes. And this is what I'm going to show you some of the metallic stuff. This is what is done by Victor. Right, goes silver. See, grown silver wire here. You have grown silver crystallites here. So you have some small. See here, you see some of them are colored. Depending on how you handle the material, you see red color, green color, blue color, depending on the particle size also, with all those things matter here. So you can grow wires, particles, lumps, all kinds of things. So you master the technique. So here, this line is the one, you don't see any absorption here. Okay, the azimate glass. Then he does something called heat treatment. You see this bits of. Because that's one way to prove that you do have nanocrystals. So this is the metallic nanocrystals. That's what you did. And also if you have metallic particles, like Sharma was telling you, see the thermostat is getting energy here, the laser. The enhances scattering here. That's what it looks like. I'm done. It all depends how much time you want. It's a very interesting talk, and most of you will be here for at least 40 weeks. So we will go for Reddy lab. It's something that I'm not sure will be interesting. But I mean, if there are one or two questions,